Hi, everyone. I would like to take this opportunity to introduce you to our speaker this month, who is Dr. Cristina Cifuentes. Cristina is a Senior Director of R&D, and she serves as a Director of Oracle Labs Australia, and is also an architect at Oracle. The lab that is headquartered in Brisbane focuses on intelligent application security, aiming at making intelligent security of applications a reality at scale. Prior to founding Oracle Labs Australia, Cristina was a principal investigator of the Parfait bug tracking project at Sun Microsystems. Today, Oracle Parfait has become the de facto tool used by thousands of Oracle developers for bug and vulnerability detection in real-world applications. Cristina's passion for tracking the big issues in the field of program analysis began with her PhD work in binary decompilation at Queensland's University of Technology. Before she joined Oracle and Sun Microsystems, Cristina also held teaching positions at major Australian universities, and she also served on the executive committees of ACM SIGPlan and IEEE Reverse Engineering. Her research interests are broadly in program analysis, binary translation, decompilation, program translation, and computer security. Besides doing lots of volunteering services for international programming languages, compiler construction, and software security communities, Cristina also spends her weekends mentoring young programmers as well. Fun fact, Cristina attended the first couple of LLVM dev meetings when they actually started in 2006 and 7. And before I wrap up, I want to congratulate Cristina Cifuentes on completing her 27 years post-PhD life. So that's a major milestone. So we are kind of celebrating her PhD anniversary in this month. I'm sure Cristina is so much beyond how I have introduced her today. Today's Meetup event is a chance for you all to know her much more. With this note, I would like to again welcome Dr. Cristina Cifuentes to the Women in Compilers and Tools Meetup series. The stage is all yours, Cristina.
Thank you, Juvie, for the nice introduction. Yeah, and as Juvie mentioned, 27 years ago in July, I submitted my PhD on decompilation. And little did I know like how all of this work was going to become relevant to the security community. So in today's talk, I want to share, it's a little bit of a journey. It's very informal talk, and I want to share about like how I used to be like a student of compilation, and these days many people know me as the mother of decompilation. And thank you, Juvie, and the whole WICT for inviting me to this meetup. So this talk is dedicated to my dad, who, when I was 15 years old, growing up in Colombia, told me that there was a future in computing. And 2 years later, I enrolled in a computer science degree in Colombia. Okay, so we're talking about decompilation today. And as you all know, we just get like binary code, right? This is binary code that executes on a machine. When you run through a disassembler, you're going to get this type of information. In this particular case, you have here a procedure. It's using the x86 architecture, and you can see that there are calls to some other procedure. In this particular case, you see two invocations to proc1, which is the same procedure. So this is a recursive procedure. And the aim of the work was to be able to take it and that type of assembly code, lift it up further so that we can get something that resembles a high-level language. In the work that I did, we were focusing a lot on the C language. And that particular procedure that you saw before is really this same procedure here. Of course, we don't have variable names, we don't have argument names, or the procedure itself doesn't have a name because there were no debug information in that particular binary that I was using. But if debug information exists, you can actually get names throughout the program. So this is the Fibonacci program, and it's just the recursion that happens in Fibonacci, what you're seeing in this particular slide. So 27 years ago, the definition that I came about was this one, that a decompiler, it's a program that reads another program that is written in machine language, and that becomes your source language. And it translates it into an equivalent program in a high-level language, which is the target language for us. So let me tell you a little bit about the background. How did I actually end up working on decompilation? During 1990, I took like compilers in the first semester, and then in second semester, I got to do a project. And this project ended up extending it during the summer break, Australian summer break, of course, which is December, January, and February. And the whole work related to an experiment on mixed compilation and interpretation. So the problem that we were looking at was that Professor John Goff's compiler for Modula-2, called the Gardens Point Modula-2 compiler, or GPM, this compiler was very popular throughout the world in various different academia settings. And it had been ported to run on multiple different Unix systems. Of course, all of the Unix systems back then were using 32 bits. And there were many requests that were coming as to, can you actually port this compiler to run on the PC? Because by then PCs had become popular, and students wanted to be able to take like the same program that they were using at university for their assignments and take it home and be able to keep on working on it. And so that was the problem that John was trying to solve. And of course, you know, like the PC back then was 16 bits. It had very limited memory, 640 kilobytes of memory. And we wanted to ensure that there were no changes to the language. Otherwise, like the assignment was not the same assignment, but we needed to be able to support the fact that there were 32-bit libraries coming from the environment. And one of the other problems was the fact that just before the compiler actually ran, just loading the first byte of source code, it was already consuming 500 kilobytes of memory. Now on the right, you can see like there were two different backends for this particular compiler. One of them was generating C code, and the second one was generating assembler code. So then the idea here, and this was purely John's idea, of course, it was to have a mixed compilation and interpretation compiler that was going to use an intermediate representation that was called decode. And therefore, we were going to be interpreting instructions from this abstract representation of decode. And we were going to do all of it through interpretation and making use of x86 assembler for that purpose. So like the front end and all of that was ported to run on Borland's Turbo C compiler. There were other changes to bring down like the amount of memory required for initialization. And so that means that we were left with 240 Ks of memory to be able to run our programs. And the idea here was also to be able to reuse like the standard linker, which was the Microsoft linker at the time, to be able to put together all of the object files and be able to use them in a seamless way. So this decode interpreter was really my compiler's project. And in the interpreter, you know, like the decode was modeled based on M code. And we used to be able to test all of it just purely by using 2 floppy disks. And those were 5.25 floppy disks back then, and be able to ship the code this way, you know, like if you run out of memory with one, you start putting in the other one, and the compiler used to know like how to deal with this. Of course, like the performance of the interpreter vary depending on the type of application, like program that you wanted to run, because we were calling into native libraries as well. And so depending on the amount of native libraries that were being used, performance would change. Overall, performance was a slowdown of 10x when you were using the dry stone benchmarks. And now for students, this was fantastic because it meant that they could actually go home and work on their PC, you know, and take their application there. So it worked really well. And we were like really happy with all of this work, you know, an idea that worked very well in practice. Of course, these days you would do things differently and you would do cheat compilation, but back then this is the approach that we used. So that background actually helped out in being able to determine what I would do for my PhD, because I found like the compilers area very interesting. I was already very familiar with assembler code. And at the time, there was a security center at the Queensland University of Technology. And that center was being driven by Professor Bill Kiley. And he was very much interested in being able to analyze binary programs because of viruses. Viruses had become very new, popular in the PC environment. And so it was something that was new. How could we actually be able to look into these pieces of code and be able to help security researchers be able to really understand what's going on in the program? So both himself and Professor John Goff put together forward this Australian Research Council grant to be able to get some funding, you know, in academia to do the project. And I joined as a PhD student to this project. Now, in the PhD work, I actually ended up focusing on a lot of different topics. There were like new techniques related to how to have an architecture for the decompiler, how to do control flow recovery, how to do data flow recovery. There was very simple type recovery. And as a result of all of this, you know, I ended up creating this DCC decompiler that was focusing on x86. It was really 80286 was what we were using back then. And the DOS operating system, because Windows was not popular yet at that point in time when I started, and being able to generate high-level C language code. Now, with the architecture of the decompiler, mainly you take, you know, like a standard compiler architecture and you go like, we're reversing everything here, but conceptually we're doing the same thing in that first we need to be able to parse the particular binary program. In order to parse the program, we first need to be able to have a loader to understand the format of the binary file, and then be able to extract, you know, like pieces that are code, pieces that are data, and so on. The parser was just going to be able to parse all of the assembly instructions, and you could emit them into assembly code. You would then want to do some semantic analysis to start lifting the level of the representation so that rather than having just assembly code, you can have a bit higher representation. And so you use a different intermediate representation there. And then you want to start looking into all of the pieces of data that are sending information through registers to be able to start collapsing that into higher level instructions. And once you have that, be able to then look at the form, the shape of the graphs to be able to understand how control flow was flowing through all of these programs. And once you have that, I was generating like C type of code. So with the high-level representation that I came up with, we really had 5 different instructions. There were assignment instructions. You can have an arithmetic expression that can be assigned to another expression. You can have a jump, so the equivalent like of a go-to. You can have a conditional jump based on a Boolean type of expression. You could also have a call to a particular location with a certain number of actual parameters. And you could have a return, and optionally that return may return a whole expression or it may return nothing, and hence the distinction between functions and procedures. Now, during that process of semantic analysis, we did end up using like these high-level pseudo instructions that they were really just transient instructions for us to be able to pull out them out of the assembly code. And they were push and pop just because they're widely used throughout the representation in assembly code, in x86 assembly code. Now, with the data flow analysis, you know, I looked into a lot of like the compilers books, right? And I already knew about like some of the compiler optimizations through John's course. We had seen some of those. The Red Dragon book became favorite type of book back then. But there were also some papers from Fran Allen and John Koch back from 1976 on data flow analysis that were also very useful for the work that I was doing. And so I took a lot of these optimizations and I started looking at them more from the point of view of like, how do we eliminate all of these registers? And what about all of these condition codes that are really relevant for conditional jumps, right? We need to be able to explicitly state what are the condition codes that get affected by each different statement so that at the time that we use them, we can actually understand like what's the relationship to other instructions. And so I ended up with, you know, like my own version of dead register elimination, dead condition code elimination, condition code propagation was being done, registers that were going into arguments, how to understand which ones are registers, which ones are being put on the stack, looking into like function return registers, like there were certain ABIs that are followed. So how to determine which ones are registers that are actually registers that are really return registers at the end of the day. And then how to do copy propagation also for the registers themselves, determining actual parameters and doing all sorts of like propagation across the procedure calls, right? So I'm just doing a few snapshots in these slides just to give you a little bit of an idea as to how it works. I'm not going to go through the whole algorithm, but if you have like this piece of code in assembly, you can see here that there's a lot of assignments being done from one register to the other. And what I started doing was, you know, just using definition use chains to be able to track, well, what are we defining and where is it going to be used? So for example, on line 28, you have a move AX DI. So that's equivalent to assigning to register AX, register DI. So here we're having a definition of register AX, and that particular definition is actually being used at line 30. Okay, so that's the notation that I'm using there. And if you start looking at all of those definition uses, and then you start propagating the registers through, you end up with this high-level instruction that I have at the end. We have an assignment to register SI of the expression DI modulus 10. Now, for condition codes, it was very important to look at them because of the conditional jumps, right? In that if you have those two instructions here, but in other cases, you may have more than 2 instructions. There was a lot of comparison of registers being done. And that comparison was really defining some condition codes. In this particular case, it was defining the sign register, the 0, the sign flag, the 0 flag, and whether there was any carry happening, so the carry flag. And then there was going to be like a jump on whether it was greater than. So it was looking at both the sign flag and the 0 flag to be able to determine this jump. So in this particular case, one kind of goes like, like the carry flag, completely irrelevant, not needed, but the other 2 flags were important, and those were the ones that were used. So what are we transferring across? We're transferring registers AX and BX to be able to do that comparison. So we have conditional jump when AX is greater than BX. Now, what about control flow? As we're putting together these higher and higher level instructions, then you need to start looking at the shape of the graphs. And there were a lot of different graphs, like on the right-hand side. Those were all the canonical graphs that I was focusing on, because you can have, like conditional branches, you can have multi-exit type of loops, you can have one-way conditional or two ways conditional if then else, or you can have the equivalent of a switch statement, right? Like an n-way conditional branch. You can have pre-tested loops or post-tested loops, right? You can have endless loops as well. So there were all of these different graphs that I was really using as a way of being able to find like what shape was really being represented, and then like nesting them, right? But of course, you see that in some cases, things like multi-level exit loops actually do end up creating other types of shapes that are not as standard. Notice though that because of compiler optimization, sometimes you end up with various different go-tos, and those type of shapes actually do exist. Now, at the bottom right-hand side, I have like this conceptual, canonical, irreducible control flow graph. And whenever you end up with that graph, there's no way that you can break it in a neat type of way. And so you have an irreducible graph, you have to emit a go-to somewhere. Now, favorite book back then was this Flow Analysis of Computer Programs by Hecht. And also there was like this other paper from 1972 from Fran Allen and John Koch as well, that was dealing with a lot of control flow type of issues. Now, there were some graphs that actually had like this shape that when you look at it, you go like, oh, what is this really? And you then realize that the compiler is doing short circuit evaluation in generating this type of code. And it actually had a condition, like if SI times 5 is equal to 50, it would go and check another condition. Otherwise, it would go directly and go to the printf statement, right? And if the second condition was also happening, it would go also to this printf statement. So that really meant that you have like one of these short-circuit evaluated conditions for an OR. And really that could be folded into a simpler graph where the expression in the conditional branch was actually summarized better and captured by this conditional OR expression. And what about like being able to then think about the decompiler, and then what do we do about all the rest of the code, the code that the developer didn't write? And that's where like some of the work from by Mike van Emmerik on compiler and library signatures came into play. Mike was working for that Australian Research Council grant, and he was focusing on, hey, what do we do about all of this other rest of the code? Because before the compiler is going to start your program, before it starts main, there's all of this other extra code that is going to be run. How do we determine where exactly is the main of the program? And what about the libraries that we're using? We're invoking into various different libraries. Where do they come from? So how do we actually determine what they are? And so Mike's work really focused on a lot of this signature generation, like being able to have signatures that actually help us determine, what are different types of compilers so that we can accurately determine where's the main for the particular program, and also various different types of libraries to have signatures for them in a machine independent type of way to be able to really map them across different compilers. And so that work was used combined with my decompiler to be able to have like a real proper solution at the end of the day. Now, for anyone here that is a PhD student, I have to tell you that my experience with submitting papers to conferences was not really good initially. I submitted, like papers to the Australian Computer Science Conference, and every year they were rejected. But I thought, like, oh, wow, that's pretty bad, because I could see some of the other PhD students, they were having their papers accepted. And then I thought, okay, I'm going to try somewhere else. I tried the Latin American Computer Science Conference, and there were 2 of my papers that were accepted there. And I thought, oh, that's kind of interesting. I had very interesting discussions with people at the conference. So then after that, I thought, well, I should try another international conference. And I tried PLDI, and my paper was rejected. And that was towards like the end of my PhD. And so I decided, okay, I'm going to actually start publishing in some of the journals, because I was seeing like a lot of like really interesting papers in journals. And my PLDI paper became the Software Practice and Experience paper that was published in 1995. That's one of the most cited papers for this work, along with my PhD dissertation. I did end up publishing the structuring, like how to do control flow analysis, in the Compiler Construction Conference in 1996. And then all the data flow, interprocedure data flow work was published in the Journal of Programming Languages, also in 1996. And here's a picture of myself and John when I received my PhD with a fluffy hat. Very happy back then. So after my PhD was completed, I went on to an academic position. And in my academic position at the University of Tasmania, I kept on doing like some decompilation work just out of interest, while I was starting to set up like a new project on binary translation. At that point in time, because of requests and because Windows had become, like the new popular operating system, I ported my decompiler from DOS to Windows. And that was done like the year after, 1995. And, I still have some of those floppies, right? And by then it was like 3.5-inch floppies, which was much better than the 5.25 floppies that used to get damaged very easily. At the time, I started receiving email from people that were overseas. And it was very interesting, because you have to realize email was new back then. And when I was doing my PhD, receiving 1 email a day, that was like, wow, I've received email. I should respond, like someone sent me an email. By the time I was at the University of Tasmania, then email was becoming, of course, like much more popular. But I started receiving like these emails from people all over the world that I didn't know about. And I thought like, oh, that's kind of interesting. They all want to know about like my papers or the thesis, or they wanted access to the source code of the decompiler. And I was also receiving like postcards, because postcards were a very popular way of asking you for a print of your paper, right? And so that was also very interesting. Now, as a result of all of these, I ended up, realizing that people were asking some similar things as well, not only like access to the papers and the publications, but also how do we port the decompiler onto a new architecture? And I would tell them, that's very easy. Just go and read the architecture manual, right? Like take on, like books this thick, just go and do it, because there's nothing hard, difficult to do in there. And that type of answer wasn't very popular because people wanted me to put it to other architectures. And so I thought, hey, if I open source the code, then that would allow other people to be able to do this work. And even better, if I create a web page, and you can see a little bit of the web pages that were written back then. Write the web page by hand, just learn a little bit of HTML, put it together, very basic, with this gray background that was so popular back then. And, created this website where I put all of my papers, all of the ideas and so on. And one day, the IT guy comes to my office and he closes the door and he sits and he says, Cristina, what do you have on that web page? And I'm like, well, just like my work on decompilation. Like, why? Because it's become the highest traffic web page for the whole department, and people are wondering what you have there. And I thought like, oh, that's hilarious, but that's really good, because from my point of view, it had actually reduced like some of the questions that were repetitions of the same, where I was cutting and pasting things on email because it was like the same question. So I thought that was great. Now, throughout the years, I ended up moving to the University of Queensland. And throughout, 1996 and 2000, I ended up maintaining this decompilation page that France Fassi had actually put together. And during this process, I ended up meeting Bill Codell. Bill had actually worked on decompilers with Maurice Halstead back in the 1960s and 70s. And so with him, we ended up adding a lot of information on like a lot of the much earlier type of decompilers that had existed. And we were always like any new information that we would find, we would put it on these pages. And this is actually a snapshot from the Wayback Machine, because I didn't keep a copy of these pages, and it would have been nice to do so, because we put a lot of work on it. Now you can see that in this one, every month we would have like, this is the site of the month. And Alan Mycroft at Cambridge was actually working on type-based decompilation, trying to focus on how do we recover types, because that was one of the topics that hardly anyone had looked into back then. And like I mentioned in my thesis, I only focused on the simple types. And these were some of the documents, that Bill would share with me. I actually met him in person in 1998 because one of the conferences sent me to Minneapolis, and he lives very close to Minneapolis. And we were like, okay, cool, let's get together. And you can see, he was involved in this concept of the inverse compiler. All of the decompilers that he was involved in, he mentioned that they were really focusing on how to migrate from one version of the current architecture to the next version. And on the bottom left-hand side, like one of his funny anecdotes, he says like the funniest, most humorous decompiler that he ever worked on was being able to decompile from a photocopy of a binary deck of a few cards, because back then the decompilers were from decks of cards. Now, while at the university, both Mike and myself, we ended up in this consultancy where, like someone contacted me on email, like, oh, I want like to be able for you to look into my program. And we weren't quite sure why. And at the end, he said like, well, it's like this program stopped working. And I just want to understand why. Like, why? Because it shouldn't. After many months, trying to go through like academia and being able to do the consultancy, at the end, we did do the consultancy. And it turns out like what we found out was that there was a time bomb in this particular binary. And the time bomb had actually been set up to become effective 30 days after an employee had left this company. And, there was only like one person working on that particular application, which was an application. It was not like a computing company. It was an application for particular work. And it meant that the whole business for this particular company had been stopped because their binary couldn't work anymore. Now, at the same time, I had already started working on binary translation. The work was started like while I was at University of Tasmania, but the bulk of the work was done at University of Queensland. And I always thought of binary translation as the cousin of decompilation, because from the front-end point of view, it was the same as a decompiler. You want to be able to take the binary program, decode it, do semantic analysis, then be able to transform it into a higher level representation. And then once you're in that higher level representation, which we call HRTL, be able to bring it down, lower it down, so that you can be able to do optimization and code generation and so on for whatever the target machine. And during this work, like back then there were a lot of retargetable compilers. That was already popular, so the concept existed. And so I thought really, like everything on the right-hand side, it's information that compiler people already know about. So we focused on the left-hand side because the easiest way to be able to do the right-hand side was for us to generate C code out of the HRTL and then let a C compiler generate everything else for us. The left-hand side, however, we wanted to be able to focus on how to do this for multiple architectures, because all of those questions that I used to get, can you put it to this architecture or the other one and so on, were like, well, we should really be looking into this. And so I was using the term resourceable and retargetable, but the term resourceable didn't become popular. Everyone would still say, okay, yeah, it's a retargetable binary translator. So in any case, there were two different levels of intermediate representation in this type of binary translators that I worked on. One was more like an RTL, register transfer type of representation that was closer to the assembler of the particular machine. And then there was that higher level one, which is where you really did like some of the understanding, like the data flow analysis, to be able to really understand what was being invoked, how to recover into higher level, and what procedure calling conventions were being used. And at the time, I met Norman Ramsey, and he was at University of Virginia. And Norm had been working with Mary Fernandez on this New Jersey Machine Code Toolkit. And what they were doing was specifying different architectures, like the assembly of different architectures. And here's snapshots for Spark and Pentium. And their aim was to be able to specify them for compiler optimization purposes and so on. And so it fits into the retargetable concept, right? And I thought like, well, this is fantastic because we want to use it for the front end of our binary translator, but we want to extend this further. And we can automatically generate a disassembler out of these specifications. And so Norma and I ended up working a lot in that area. And we started then focusing on some of the other parts, right? Like there's multiple different types of binary file formats. There was like the PE was the one that was being used in Windows, but then on Spark, you were using a different representation, and then on MIPS was a different one, and so on. So we thought, okay, we need to start working on how do we specify all of these different representations to be able to do it in a more generic way. And so this was work with my student, David Ang, where we actually specified 3 different representations, and we came up with this simple retargetable loader. And this was David Ang's honors project, so final year for here project. With student Shane Sendall, we ended up working on how to extend to semantics. So we need to be able to understand not just that these are assembly instructions, but how do we add some information that relates to the semantics of those assembly instructions? And you can see here that we started initially with the object set specification to be able to specify everything, right? And that was purely like an influence from the University of Queensland, the fact that all of the verification people back then were using object set for specification. So then that's what we used. But then we went, after a while, we went and said, like, what do we do with these specifications? Because we need to be able to convert them into something that is going to be more amenable to automation from a program point of view, right? And so those specifications ended up being converted into a lot of different pieces of code that is just like a way for us to declare, right? Like if you have an add instruction, well, it's going to be the equivalent of the plus, right? Like an addition. If you have like condition codes, well, this is what they mean, right? A branch always means it's a yes, it always happens. A branch never, it's a 0, it never branch. A branch on not equal to, it means that it's the negation of the 0 flag and so on. So that's the type of specification language that we ended up creating. So then this complemented Norm's SLED language, and now we had something more powerful to reason with. And then we also started looking into various different procedural calling conventions, right? Because you have, like, when you're going to invoke a particular call, there's prologues and there are epilogues that get set up by the compiler. So we needed to be able to specify them and how our parameters being passed as well. So these were just 2 different snapshots here from the PAL language that we created for it. And this was work with my student, Doug Simon. That work, actually, we only ended up putting it into a technical report. And then we also even extended this, like when Trent Waddington, another student, actually joined the project, he was interested in being able to generate Java bytecode because Java had started becoming something new, something that a lot of people were talking about. And we looked at it and we're like, whoa, but that's bytecode. You can actually, you know, transform all of these into bytecode. And so we had an unpublished write-up, actually, that we put together. The work was at prototype level, and I don't think we ever released this part of the work. Now, at the same time, while we were doing this, other people started like working on the compilation, of course. And in 1998, like one day I get this thank you email. And I was like, oh, what's source again? And what is this? Looked it up. Well, it turns out like the thank you was because they had used like my PhD thesis as a way of them being able to set up their startup company around Java decompiler. And so they created this Java decompiler called Source Again. And there's like a snapshot of one of their announcements from their company, Fast Software. And they said, like whenever you're in the Silicon Valley, let me know and we'll go out for lunch. And so one day, yeah, we did end up going out for lunch. Now, I also ended up meeting people from the source recovery company. They had sent me an email because they were working on decompilers to be able to help with the year 2000 bug. I don't know how many of you remember the Y2K problem, but that was like a big thing back then, close to the year 2000, all of these programs that are going to break and so on. So a lot of their work was around recovering COBOL, assembler, MVS, and a lot of these acronyms that you see on this slide. And what was a little bit different is like, this went on for several years, and they wanted like to be able to buy DCC, right? And like I was like thinking, like, how do you buy DCC? I mean, I had open sourced it, I had put it under a GPL license so that people could not use it commercially. And we thought like, yeah, I don't know. In the end, like, of course, like we didn't end up collaborating in any way, but it was just interesting to hear about like some of their decompilers and how they were actually structuring their work. And because, like we were so much interested in this work, we ended up creating this workshop on decompilation techniques. And the one and only workshop on decompilation techniques back then was the one that we ran in 2001. And it was co-located with the Working Conference on Reverse Engineering. And in this photo, you see Mike Van Emmerich to the left. You see Ilfak Gilfanov from IDA Pro fame, right? IDA Pro, right? Like the disassembler to use, right? Like back then and even today. And then you see myself, and to the right, you see Trent Waddington. And for us, it was like, wow, we're going to get to meet Ilfak at this workshop because he was presenting on a type system that he had been working on for disassembly. And we were presenting on the idea of being able to integrate a debugger along the decompiler so that as you're debugging, we could be showing you snippets of decompiled code. And our work was just like at the idea level. And what was fantastic for us to discuss was the fact that Ilfak had already been having ideas and some initial work on a decompiler of his own. And so we exchanged a lot of ideas on this area. And as some of you may know, like Ilfak does have a decompiler these days that he makes available commercially as well. Now, throughout that process, I had already moved to the US. And in 2001, it was actually right after, like the month after this workshop, like the .com had crashed, projects started being canceled, and my binary translation project was canceled. So I ended up working on other type of projects that, I'm not going to discuss like in this talk, other than say that there were other involvements that I had in this area. I co-supervised like one of John's students, Jens Stroger, on looking into virtual tables and how to come up with a higher level representation and abstraction for it, for virtual tables. At the same time, like both Mike and Trent ended up writing like their own new decompiler called Boomerang. And the idea here is that this was going to be the next generation implementation of DCC. It was using like a lot of the work from UQBT, from the front end of the binary translation work. It was using library signatures. They were focusing on Spark, Pentium, generating C code. Their analysis was focusing on live range splitting, and they tell me it worked like really, really well. And it was also for them a ground to be able to experiment with SSA form. And, you know, like Mike was so into this area that he ended up doing a PhD in this area. A lot of the work focusing on the SSA representation, because it really simplified a lot, like the type of data flow analysis that was being done. And it also helped with being able to do type analysis, to do that type inference analysis. There was also some work that he did on the indirect jumps and calls, because virtual function call tables, yeah, that was like a big issue for compilers, of course. Now, while I was in the US, there was this other consultancy that I did where there was a company that was interested in getting some training on decompilation for binaries for an on-chip processor. And they wanted to develop their own decompilation engine. So they made available, you know, like the instruction set and manuals and so on. Because I always ask like people, instruction set, what's the manual? All the information is there, you know, like one can understand it from there, right? And what was very interesting was that as a starting point, I used the IDA Pro disassembler to be able to look at this. And sure enough, like it worked really well. And so then from there onwards, you know, it became very easy to be able to explain the rest of the decompilation process, because you had, you know, like an initial setup for them. You don't need to learn the rest, how to disassemble and so on. You can start from the fact that a disassembly can be created for you, and then you can add the rest for the decompilation engine. So that was pretty interesting. And then in 2005, I met Chris Weissapol. And Chris, you know, was working at Symantec at the time. And his team had been developing a vulnerability analyzer based on binary decompilation. And he had told me, you know, like we've used like all of these ideas and so on from your PhD thesis. And we want to be able to branch out of Symantec as a startup company. Can you provide some feedback to our venture capital investor and so on? So I had like interesting discussions with them. And at the end of the day, you know, like the quote that I have here, that your opinion was instrumental in helping me make my decision to invest in Veracode, came from the venture capital investor. And as you all know, like Veracode was founded in 2005. And, you know, in 2006, I actually joined their board of advisors, and I was there for several years on that board. And Veracode is still alive to this date. Now, throughout all of these years, you know, it has been interesting getting like a lot of different quotes that people, you know, like when they know who I am, you know, they start telling you about like work that they've done and so on. So when I go to conferences and workshops, you know, there's a lot of this two-way communication in that people tell me what they've done in this area, and they also want to know like, how did you do this, or how would you do this, right? And those conversations are super cool. And there have also been like the one-way communications where they know that I'm Cristina, they go, they start asking me all of these questions about decompilation, but they don't want to tell me what they're working on. And you go like, oh, that's a very interesting one-way street sometimes. Throughout the years, I've ended up reviewing many papers on decompilation. And perhaps the coolest introduction that I've ever received was in 2018, Rich Johnson had completed his training on Fascinat, hacking the box in Singapore. And then we were getting together for dinner and he says, let's go and chat with some of these hacking the box guys. And then they go like, oh, do you guys remember like the compilation of binary programs paper? Well, the compilation of binary program paper, right? So referring to the software practice and experience paper. And they're like, yeah, the paper by Cristina. And he's like, here's Cristina. We were like, oh, that was so cool. We all had like a good laugh out of that one. Now, the next year, the NSA released their decompiler called Gitra. And they made their decompiler open source later that year. And, you know, that resulted on like a lot of talk about like where did some of the ideas come from and so on, and the timing and so on. But I also went like, yeah, okay, yeah, I also do remember some one-way communication type of questions. So it was really interesting, you know, like when this came out, you know, we thought like, oh, this is really good for the community because now there's like an open source industrial strength type of decompiler that the community can actually work with. And it encapsulates even the ideas of the debugger support that for us were ideas back in 2001. And so the next year, myself, along with Mahim Chandramohan and our student Haoxi Tan from the University of Queensland, we thought, let's start making use of these and let's start focusing on how do we create an infrastructure to fully automate extraction of indicators of compromise from malware and from Windows malware in particular. So we took Gitra, right? Like Gitra was the incentive to do this. And here's like a decompilation of Gitra of the WannaCry malware, just like the initial snapshot. But in our infrastructure, what we did was to put together a variety of different types of tools. So we had a way to be able to take any number of binaries that you may have. They may be malware or they may not be malware. You know, you have binaries, put all the binaries through this pipeline, and then be able to run bin walk through them, because sometimes you need to unpack some of the binaries and then run both Gitra and Radare2 as decompilers and any other tool that you can integrate into the framework. And then look into the threat intelligence APIs like ThreatMiner, OTX, VirusTotal, and be able to start extracting more information that way so that then we can generate information for a security analyst. And the type of information that this infrastructure automatically will generate to you, for you, yeah, looks like this. You know, you can dump JSON for, here's like the report that Gitra has generated, that Radare2 has generated, and so on. Here's like our matching to Kappa rules. And that's very useful information as well from a threat intelligence point of view. Also, it generates for you interesting URLs so that you can focus on, wow, some of these URLs, we may actually need to be looking into them more closely, right? As well as interesting strings that people tend to use to be able to understand indicators of compromise in some cases, right? So this whole infrastructure called ColdPress is open source. It's available on GitHub at the UQ Cyber website. So now, let me start wrapping up. When I looked back, when I was invited to give this talk, I went back and I started looking at, wow, what has been done? A lot has happened since the 27 years ago when I published my thesis. And I feel that there are two areas where there's still like a lot of further work that can be done. Decompilation is not an easy topic, you know, it can be very challenging. But certainly being able to do alias analysis has been one of the big areas that not many people have really tackled. And how you do alias analysis in an interprocedural, context-sensitive, path-sensitive way, that becomes important. And that topic on its own, it's a whole PhD. The other area that I would say also needs some further development is the whole area of type recovery. So how do you recover to not only like the basic types, but also like more complex structures, right? Like you're going to have classes. So how do you recover into a class that is really more representative of your object-oriented language if you're using C++ or something else? Now, throughout the last 20 years, I have been involved in a lot of different type of compilation projects. I'm listing them, all of them here, but I wanted to highlight, like, for this audience, that the whole of the infrastructure for Parfait, a static code analysis tool to be able to find bugs and vulnerabilities in source code, was built on top of LLVM. And that's how I ended up attending some of the first LLVM developer meetings, because to us, we had evaluated various different infrastructures and we thought, LLVM is the way for us to go. And we're so happy that we made the right decision, because Parfait is a project, that there's a team at Oracle that works on that project. I'm just on an advisory level these days, but the tool is being used significantly throughout the company. And the choice of the infrastructure is a really, really important one, because you don't want to be migrating to a different infrastructure later on. Now, when Bill Codell and I looked back at all of the work that had been done in the earlier years, we thought that the work that stood the most to us was the work by Maurice Halstead. And that work extended for many years, from 1960s all the way to 1978. You have here on the right-hand side my written notes from when I met with Bill in 1998. And we were like, these are bits and pieces that we need to fix. Don't ask me why the printout cut off part of like the title. But at the time, we had decided that, the most influential work had been the work by Maurice Halstead. So back then, we named him the father of decompilation. And that was posted, like on the decompilation page. Now, these days, the term Mother of Decompilation has been quoted, and that has been due to all of this work based on my PhD thesis. And with that, I conclude my talk. Thank you.
Wow, that was incredible. Thank you so much, Cristina, for sharing your entire journey with us. There were so many anecdotes that you shared, and they were very interesting. So thank you for sharing all of those. It was so cool to see, a lot of different things. For instance, you shared that there were deck of cards that you used to, run your actual decompiler with the collaborations that you made. And again, there was another, important thing that came out, that as soon as you open sourced your first decompiler that you worked on during your PhD, people actually started to reach out and they started using your tool right away, and they started extending it for different architectures. And today we all, in all the conferences and, different communities, when they gather together, everyone is, trying to encourage open source culture quite a lot. I mean, it's happening a lot more, than in the past, obviously, but it's incredible to see, like, you did put in efforts to make your work open source back in 90s. So that's amazing.
Yeah, I thought like it was like the only way, right? Like back
Yeah.
then, I did have a law colleague from the University of Tasmania, Anne Fitzgerald, and she was the one that helped me understand like the different licenses, right? Because I knew nothing about licenses back then.
Yeah.
Yeah.
That's amazing. Yeah, so with this, we are now opening up the question and answer session. So to the attendees, please feel free to ask questions yourself, or if you just want to post it in the chat section, please do that, and I can ask the questions on your behalf. So there is a question in the audience. Do you know of any good ways to recover the control flow in the presence of continuations of an event loop?
I haven't looked into that. I don't know off the top of my head any papers. It doesn't mean that they don't exist. But I haven't looked into it. Yeah.
Okay, that's fine. Are there more questions? Otherwise, I can get started. I have a lot of things to ask just to know you more.
Hey, Christina, I had a question. So you mentioned that one of the motivations for your work was because of viruses and to figure out what they were doing. Is the opposite also possible, where attackers can now look at binaries and decompile it, and then they might be able to figure out vulnerabilities in our code? And if that is, are there strategies to mitigate those kind of things?
Right. Yeah. Like when you decompile, I mean, anyone that works in the reverse engineering community with binaries, they do end up decompiling binaries for various different purposes, right? So someone could use it like to be able to find vulnerabilities. They do need to add a lot more, or they do need to prod more, right? But a lot of like reverse engineering is a manual process enhanced with tools. So yeah, it can be used that way, right? It can also be used to be able to find what you need to fix, right? So yeah.
So, I guess my follow-up question there was that, okay, of course, not leaving vulnerabilities is the best strategy, of course, but are there some programming techniques that, kind of cause decompilation to fail, so that, certain, really secure parts of our code base, we can make sure that it is, that you're not able to decompile it?
Oh, right. Yeah, actually, yeah, I didn't mention this. Yeah, but being able to have like a very good decompilation of like a large binary or any reasonable size program is very hard, because you have indirect jumps, right? So whenever you have an indirect jump, or if you have an indirect call, it's very hard to be able to know statically where that's going to go. So where is that jumping to? And that's why, like, like for object-oriented language, for example, where you have virtual tables, well, where exactly is it going to jump to? It's very hard to be able to know statically. So, like in practice, when a decompilation is done, normally like there are some pieces of code where the decompilation looks all right, and there are other pieces of code where it may miss, because if you have an indirect jump, it may be that the decompiler doesn't really know where else to go, right? And there's where like people start working with manual type of techniques to be able to understand like where should it jump to, and you know, it becomes a manual process, right?
Okay, got it. Yeah.
Yeah. And it's the same with types, right? That in terms of types, you know, like the decompiler is really giving you kind of like the more basic types, and being able to get like to, you know, like types as you see them in your high level language, right? That is pretty complicated as well.
Right. Yeah, I can imagine. Like a lot of that is sugar too, right? Which you cannot get on top of, get like even after like the pre-processing and the next couple of steps are lost. So there is no way we can recover that from the binary.
Oh, sure. Yeah. Yeah, definitely. Yeah.
Thank you, Cristina.
Okay.
Welcome.
So we have another question from the attendees. This is from Michelle Strout. There's a decompilation for finding security issues. What have you seen in terms of decompilation for the performance improvement?
Hi, Michelle. Yeah. Yeah. So for performance improvement, I don't think that I have seen any myself. I mean, we did discuss this in terms of like the fact that one could regenerate, right? Like just use like get the code to some high level representation to then regenerate the code using like whatever, you know, like your C compiler or something, and really use like higher levels of optimization. But we never actually looked into it, and I'm not familiar with any papers in that area. I have heard several different groups talking about it, but I haven't seen like the papers in that space. Sure.
All right. There's another follow-up question from Aaron. They're asking, do you ever mix static and dynamic analysis to get a better decompilation?
Right. Yeah. So if you can actually have a system where you do static and then you have a dynamic view of the world, right? Then you can capture what bits and pieces are missing, right? So my example of an indirect jump, dynamically you would know where it's actually jumping to. So then you would know, oh, that's a new entry point. And then you can map that. If you can map that entry point in memory back to where it is in the binary, you would then be able to start, you know, like running your decompiler from there, right? Like to be able to get that code and feed it into back into the rest of your static analysis. So it is possible to do it. I know for binary translation, we were doing that because we, you know, at University of Queensland, we were focusing purely on static. But then once I was at Sun Microsystems, was focusing on dynamic, right? And the idea was to be able to bridge and get the best out of it. Yeah.
Cool. So there's another question from the attendees, JC. They want to know if an individual wants to study decompilation and work on novel techniques for improving the areas such as type analysis and alias analysis, do you think a PhD education is necessary? And what do you recommend for someone who wants to study decompilation techniques but is unsure if they want to return to academia for that?
Right. Well, I guess sometimes it's personal preference, right? But I think, you know, like to be able to work like on some of these techniques, it really depends, you know, like you need to have kind of like an advisor that knows about alias analysis, for example, or how to look at type analysis, type inference analysis in particular, right? And you do tend to find a lot of people that know about these areas in academia. So you know that's why like the PhD route kind of like makes sense from that point of view. But of course, there's also people in industry that know about these techniques, right? And it depends how much you yourself actually understand and know about that area to be able to be guided the right way. Like, so if you have like some mentors that actually know about some of these techniques, they can actually point you to read this, read that, right? So that it helps you be able to further develop your own ideas and be able to bring them up. So it really depends on your own experience, right? If you're already someone that has been working in industry, it may be that you can do it yourself if you have some relevant mentors in that space, or it may be that you could do it part-time. I know that that's how Mike Van Emmerich ended up doing part-time at some point in time while he was working and completing PhD.
Yeah, that's amazing to know. There are different ways people can always pursue their passion for.
Yeah.
Okay. This question, that I particularly wanted to ask, not just for me, but in general for the researchers and learners out there. So your PhD research topic, as you yourself also mentioned, was on the binary decompilation, and that topic was not popular in the 90s. And today you have earned the title of Mother of Decompilation. We would like to know, if you look back in the past, how does it feel today and how it felt back then when you struggled with the rejections of papers, right? And today, anyone just looks up on Google Scholar, you have around 4,000 citations, and I'm sure there are so many which are not listed out there because this work kind of forked out in the times when there were no, such citations mentioned to the work and everything. Like even a lot of companies have used your work. So what really kept you going at that time, bearing with so many rejections, and what message would you like to give to the researchers, learners, or anybody out there who is pursuing the passion for their area of interest, but sometimes, it's hard to just get the word out there and to get your work well received from the community as well?
Yeah. Yeah, that's a nice question, because so I think initially, like when the papers were being rejected, initially I thought it had to do more with like, I don't know how to write and English is not my first language, right? So I thought it had to do something with that. I did fix some of that, like by having a technical writer actually working with me and then realizing it was not that. It was just that the papers were not being accepted because the way that one professor told me one day was that your work was really early. Because in the 2000s, the security community started picking up on this. But, like I did my work in the 90s. So that's really why like it was hard to publish in this space. Now, why, like how to continue and so on. I mean, I found the area like very, very interesting, as in, I would spend days on end just working on, when it was control flow analysis, I was reading all sorts of graph algorithms and so on. I just found it fascinating. So I was just having a lot of fun doing the work. And the fact that, at the end of the day, you need papers like to graduate and so on, then it's like, oh, okay, I better see how I can actually make, some papers a reality. And there's where I started like looking into like journals, right? That I went like, why is it that I'm reading like a lot of papers that were actually published in journals? It doesn't necessarily only need to be conferences. And I started like looking into that and realizing, oh, actually you can tell a better story in some of these journals because you have more pages for starters. And that made it easier in a way, like to be able to explain the work, because no one was familiar with the work. So it kind of like, it needed like better explanation rather than, oh, it's continuation of whatever other type of work that people are already familiar with. So I think, you know, like if you have a passion for a particular area, there's always going to be ways of continuing doing that work. That has been my experience, you know, like there's been many different projects throughout the years, and, you know, you can make it happen. That's always been like the way that I look at things, if I'm really interested, right, like in that particular topic.
Yeah, that's fantastic. I think journals is for sure one of the key answers for us. You know, if anything that we want to say in more words, or we want to create a better pitch, I think sometimes we miss out on doing it through the conference papers. But I think, yes, journals do allow us. And again,
That's right. Yeah. And actually, like I forgot to tell like this little story, like with the software practice and experience paper. What was very interesting to me was that I started getting all these people, right, that had read that paper, sending me email. And I was like, wow, these people are all over the world, right? And one of my friends, Cesar Munoz, whom I had studied with in Colombia, he was doing his PhD in France at INRIA. And he sent me an email. He said, Cristina, I was sitting in the bus going to INRIA, and I was reading like this paper that the person next to me was reading because it was very interesting. And then, you know, I asked him, can I see like the title so I can download it? And then I see that the title is it's you, Cristina, you're the compilation paper. And I thought, oh, that's fantastic, because I think the work was actually more disseminated by having it in a journal. That has been my conclusion, yeah, over the years. And of course, like these days, you can just Google publications, but at the time, it was more disseminated because of the journal publication.
True. Yeah, that's great. I think it's like everyone should follow their passion and just continue to work and not lose or get disheartened, basically, if we get rejected.
Right. Yeah.
That's great. If there are more questions from the attendees, please go on and ask.
I have an observation. Christina, it's a very beautiful talk. So I've heard about you from Tent. I work at Veracode. And so.
Oh, wow.
So yeah, I actually work on one part of the static analysis, and Trent works with us. He's in static analysis team, and decompilation is one of our phase for our static for security analysis. And yeah, I've heard about it, and now I'm just connecting the decompilation thing with you, and so it's very interesting to know and your talk. Thank you.
Right. Yeah. And I got to just quickly send a note to Chris, you know, like over the weekend, just to make sure he was happy me telling the background story. And he was more than happy. Yeah. Good to meet you.
Nice meeting you. Thanks.
Okay. So another question. So you spent your initial years, in academia, in different universities of Australia, and then you moved back to the industry. So usually, it just gets too hard for someone to figure out, switching between academia and industry. One, why did you make that move at that time? Or you spent like a longer time in the industry, and even today you are in the industry, but at the same time you're still an adjunct professor in another university at Australia. So how did this whole happen? How do you manage two different responsibilities together? And how does one make a mind about, like, okay, this is why, and this is how and when I can make a move to academia versus industry and vice versa?
Right. Yeah. Well, we have Michelle in the audience who also did that move recently. Yeah. But for me, it was because what I ended up realizing while I was in academia, I had been in academia for 5 years, right? And I was working on binary translation. And I had even been approached by venture capital to be able to convert my binary translation work into like a commercial type of work, right? And back then, I didn't know much about, startup companies and so on. And the deal was also not very good because you had to keep on doing all your teaching plus be involved in the company. I was like, yeah, right. I can hardly do this, right? So what I found interesting in my case was that I was invited by Sun Microsystems. Neil actually invited me to do a sabbatical leave there with them. And that actually helped me really cement and understand the difference between just doing the work in academia as opposed to the next level. How do you take that work to the next level so that people can actually use it in practice, right? And they were interested like in the binary translation work at the time. And so at the end, of my 1 year sabbatical leave, I ended up staying in academia because I really wanted to see it through, right? I wanted to make it more, because I knew that in academia, once you reach a certain level of the ideas, then it was like, you can't just keep on working on that. You need to like, what's the next grant, right? And the next grant, and what's the next project, and so on. And, taking that sabbatical leave in industry really helped me understand that difference. If I want to take it to the next level, I really need to be in industrial research, which is what I joined. And yeah, that has helped, right?
Interesting.
Yeah.
So
maybe Michelle wants to tell her story.
yeah, sure, please. We would love to hear from you as well, Michelle.
Yeah, it is fun. Like right now, I'm definitely both in academia and in industry because I'm on a leave of absence. But I completely see what Cristina is saying. After 16 years in academia, now in industry, I can see how there's more of a possibility of people starting to use the work, the things that the group is working on.
Interesting. So
Yeah.
do you think like if, there were more tie-ups, for, let's say, the young professors who start their career in academia, of course. So if they have more tie-ups with the industry at that time, or if they can, take periodic sabbaticals in between to go to the industry and let their work, get into the real world, would that be, can that work out ever? Just curious, like I have no, idea about the dynamics at all. Just curious to know.
I mean, I think it happens a lot. I think that people do sabbaticals in industry a lot, and they get that opportunity to see how their research is able to affect a lot more people. And then sometimes they come back to academia and sometimes they don't. And I think everybody kind of chooses what works best for them.
Sure.
So I think the key thing is there's so many options for people in compilers and in computer science in general. So that's really nice, is to realize that we all have so many options and can really think about like, what do we want to do?
Yeah.
I definitely cannot agree more. Yeah. And I know of many professors that they're doing sabbaticals, right? Like in industry, and they go back, but like it brings that also that other way of thinking to them when they go back to academia, right? Which is great, so the cross-pollination really, really helps overall.
Yeah, I think my follow-up question anyways was about, one is for sure this idea of, when you research something, if it actually gets to, be more beneficial to the real world out there, that's, the best reward one can get. But there's another side of being in academia, that you get to teach a lot of students, right? So that's like one of the most valuable contributions the professors actually make by being in academia. So I was just curious, like, for instance, you have now returned back to academia as an adjunct professor, Cristina. Like, what really, makes you balance this whole juggling between industry responsibilities, because you have a lot to handle there as well, and then you are spending your weekends mentoring all these young programmers. It's just fantastic to see, like, how do you manage so much, and what really makes you so happy about this teaching experience?
Yeah, well, I have to say, like in my adjunct professor role, I don't end up doing a lot of teaching because we end up collaborating a lot with the students, right? Okay. So I do tend to give like one lecture per semester. So that's not a lot, right? But the collaboration with the students is something that is fantastic, because it allows us to be able to bring this other way of thinking, right, to the students, and they realize like, oh wow, like this whole other world, because it's very different, right? Like if you do the project just purely in academia, as opposed to you do it as a mix of academia and industry working together, right? Yeah. I can say that the teaching has helped me a lot throughout my career in being able to explain things to different audiences. And so that was a very good learning for me from being like 5 years in academia, like with normal standard teaching load, right? Yeah.
So coming to your another very successful project of Recal Parfait. So how did this idea of the project led to such scalability that today, it has become a de facto tool, and thousands of developers are using this tool on a daily basis? So I'm sure there must have been like a lot of challenges. Would you like to share something on a high level, like what were the major challenges, and how did you, try to solve those as a team or as an architect of this whole big project?
Sorry, with Parfait, I had muted myself. Sorry. With Parfait, we realized that everyone was doing, at the time, startup companies that were focusing on static analysis of code, they were doing like full global data flow analysis. And we thought, but we're trying to find bugs, and we don't need the work to be done like that. And so it was more the realization that you can actually do the analysis in a demand-driven way, right? So you have a bug at a particular location where it's going to be exposed, right? Buffer overflow will happen, well, whenever you're dereferencing an array. How about we do demand-driven from that dereference backwards to be able to find the relevant subset of instructions that need to be analyzed? And that's what allowed us to get scalability. That completely makes like a huge difference in your static analyzer.
Interesting. Yeah.
Yeah.
That's amazing. There's a question on, can we sign up for?
Oh yeah, there's a question about mentoring. Yes. Yeah, more than happy to talk to you. I'm Reed fan. Yeah, always happy like to help mentor students. Yeah, students and also people in which I do it all the time. Yeah. Like Julie would have my email address.
Yes, I absolutely have it, and I'm very happy to tell you that I'm also mentored by Cristina through Sick Plan long-term mentorship program. So yes, I owe a lot to Cristina for finishing my PhD as well.
Oh, no, it's all your good work, Juby. It was all there.
You have been there for me, for sure. So thank you for that.
You're welcome.
A few more questions, if you don't mind me asking. I think I'm always curious to find out more. Can I ask if you don't mind?
Yeah, sure.
Okay, so a few more questions on navigating the career ladder in industry in particular. So how do the roles and responsibilities vary as someone goes up from being, let's say, a software engineer to senior software engineer to becoming a manager, director, or an architect, one day? So I would like to learn more about that, about how do the roles and responsibilities vary. And second, what advice would you give to the industry people, who aim to grow up in their career, and how should one plan for this, career growth in the industry?
Right. So in industry, like the roles are very well defined. Normally, like there's the technical track and the managerial track. And with the technical track, I mean, like one starts as junior and then starts becoming senior and then more senior. And in our case, like the last level is becoming a full architect, right? Purely on a technical side. So there's 6 different levels. And initially, like the more junior roles are more about like being able to work in a team. So you get assigned certain tasks and you're able to deliver those tasks. You do need some help mentoring from the rest of the team. But then once you get like to the senior roles, it's more about like you're also able to be helping out with the designs, being able to own, like more complex parts of a project, being able to work with others. And then as you keep on going up, like being able to develop projects that are strategic to the company, right? So you're not just working with your team, you're actually influencing outside of the team, right? Like to other organizations. And so those are like the 2 most technical roles, senior roles are like that at Oracle. And it was the same at Sun, yeah. And then managerial, like manager or director, VP, all of these, it's a parallel track, right? And I have done both, as in, like I started technical, then I went managerial, then I went back to technical, then I ended up as an architect, but I had people reporting to me, and eventually I ended up as director, yeah.
So any word of advice on like, for the beginners who have entered into the industry after the undergrad or grad schools and so on? So how should one set a vision, to aim for like next role up? Because let's say if we start as a, programmer or as a developer, in the industry, we get too much involved into our day-to-day programming challenges at times. And then we are like, stick to all those release schedules of our team's project that we work for. But then sometimes we end up losing that higher perspective of things, that where are we leading to? So how should one aim towards keeping that bigger picture also in their mind, so that they can keep growing technically and personally as well?
Right, like so there's set criteria, right, for each of the different levels. And it's a matter of knowing like what the criteria is. Criteria is always posted, in all of the companies that we work on. So it's a matter of understanding what the criteria is and being able to work with your manager on it, right? In that, if you feel, for example, that the tasks that you're being given, they've become very simple for you, it's very clear that you're ready to be taking on something more challenging, right? So that's like the type of discussion that you can have with your manager. Taking on more challenging work, then at the end of the day, is going to lead up to, you end up working kind of like at the next level, right? Which kind of like points towards that. So so yeah, so always like my advice has been for everyone to be able to understand what is expected from your level, what's expected from the next one, so that you know what's the difference, right? Because it's not number of years, right? It's complexity of the work, and in some cases, like influence and so on, right? Yeah. And then discuss with your manager.
Yeah, thank you. That's a great advice. I think we'd like to wrap up with one final question. Tell us about, tell us something about yourself that very few people know. So today, a lot more people would know about you. It can be anything, just a fun question.
Oh, maybe not as fun, but my dad is in hospital, and
oh, you're so sorry.
like, yeah, dedicating this talk to him. I told him the other day I was going to give this talk, and he said, "That's really good, like giving a talk where you're actually also helping other people learn more about certain areas. That's a very good thing to do." He always supported community type of work, right? And he saw this talk kind of like as community type of work in his words. Yeah.
Yeah. Very sorry to hear about your dad, but we all will definitely keep him in our prayers, in our good thoughts, so he can recover soon.
Yeah, thank you. Thank you.
Yeah, I think we are all good. And thank you so much for sharing such an interesting and amazing journey of your binary decompilation and a lot more beyond your technical growth that you have accomplished, all the success ventures that you have accomplished in your career. It's been fantastic to meet you, Cristina, and thank you.
Yeah, you're welcome. Thank you, everyone. And thank you for inviting me. This was a lot of fun to put together and remember so many things.
Thank you. Thank you so much to all the people who attended our meetup today. So we meet every last Thursday of each month. So tune in to our meetup page. We'll post our next speaker for the August month as well. Thank you.